Two vectors are parallel if they have the same ratio of components, so the same ratio of I to j to k. We can show that they're parallel if one vector is a multiple of the other. So if I was to find A and B so that A for B is parallel to 3, 6, 9, two statements that I can make that are true is that some multiple lambda of A for B equals my vector 3, 6, 9, minus 9. A completely equivalent statement would be that my vector A for B is some other multiple, so this would be a different lambda, is some multiple of 3, 6, minus 9. Either of these are true. In each case, the lambda will be different. So we can actually explore, let's go with this one on the left, and find, multiply out this lambda and find our three equations. So I have lambda A equals 3, that's by multiplying 3 by lambda. I'm just looking at the I component here. Then for the j component, I have 4 lambda equals 6, and then I have lambda times b equals minus 9. Now in this case it's fairly straightforward, I can just solve for that lambda. So lambda equals, rearranging this middle equation, lambda equals 6 divided by 4, which equals 3 over 2, we'll call that 1.5. So lambda equals 1.5, so we can start having a look in solving for these other unknowns. So 1.5a instead of lambda a equals 3, a equals 3 divided by 1.5, so a equals 30 divided by 15 equals 2. And then last but not least we have, let's go with a nice orange, I have 1.5b equals negative 9, b equals, we'll just do that one on a calculator, negative 9 divided by 1.5, negative 9 divided by 1.5 is negative 6, negative 6. And if we wanted to, we could back substitute and see that this is the case. So if I set this equal to, if I had 1.5 multiplies, what do we have here? 3, 4, 3 times, yeah, and then b is negative 6. This should multiply out to get us to, hang on, oh, sorry, a equals, what does a equal? 2, a equals 2, not 3, that's why it didn't work. 2 for negative 6 should multiply out and give us this vector here. Okay, let's have a look at this one. Find a so that 2a 6 minus 3 is parallel to 4, 12, negative 6. So I know if they're parallel, there'll be some multiple of this vector, 6 minus 3, will be equal to 4, 12, minus 6. So 2a lambda, lambda 6 lambda, minus 3 lambda, equals 4, equals 12, equals minus 6. So I can say lambda equals 2 here. And we can check that that works on this one. So does that work? Minus 3 times 2. Yep, that does equal minus 6. So our lambda works, it's consistent. So lambda equals 2. So then looking at this top equation, I have 2 times a equals 4. So 4a equals 4. So a must equal 1. So my vector is now 2a, well, we can say 2 multiplies 1, 6 minus 3. And does that equal 4, 12? Oh, that's 2 times a, so that's 2 there. Excuse me, I'm making lots of mistakes. 2 times a, so that's 2. If we multiply this through, do we get to our original vector? Yeah, we do. 2 times 2 is 4, 2 times 6 is 12, 2 times minus 3 is minus 6. So this value of lambda works. And then I think, last but not least, we have this one. Find a such that p plus q is parallel to 3, 6, 1. Well, let's firstly work out p plus q. So p plus q is going to be 2a minus 1 plus 1, 3, 2. So we're just going to add along the rows. That's 2i plus 1i gives us 3i. A plus 3 gives us a plus 3j. Minus 1 plus 2 is 1k. So this is p plus q. P plus q is parallel to this 3, 6, 1. So some multiple, some unknown multiple of 3, a plus 3, and 1 is equal to 3, 6, 1. So 3 lambda equals 3. Lambda multiplying a plus 3 equals 6. And then lambda equals 1. So I can see from these top two equations that lambda equals 1. This is already lambda equals 1 on the bottom there. So if lambda equals 1, then I can carry on with this middle equation, and I can just say 1 times a plus 3 equals 6, so a must equal 3. We could have a look at that. So let's pop a as 3 in here. So I have 1 times by 3, 3 plus 3, and 1. Does that equal this? Yes, it does. 1 times 3 is 3, 3 plus 3 is 6, 1 times 1 is 1, so this works. Okay, and let's look at this. Now, points are collinear if they're on the same straight line. We can show that 3 points are collinear if we find any two of the vectors AB, AC, and BC, and show that any two of those vectors are parallel. If any two of those vectors are parallel, because they share a point, so for example, if we found these first two, A, B, and AC, we could see they both pass through the point A. If they're parallel and they both pass through the same point, they must all be on the same line, because if it skewers those 2 points, it's going to skewer the other two. Equally, if I was to find the second two, so if I found AC and BC and showed that those two vectors were parallel, I could say, okay, they're parallel and they go through that shared point C, so they must be collinear. They must all be on that same line. So we're either finding AB, AC, or AB, AC, or BC. If they are parallel, then they're collinear. So it's either AB, AC, or BC. So let's look at these questions. Determine whether the points A, B, C are collinear. So we could find either AB and AC, or we could find BC. And if we can show that if we find any two of these vectors and show that they're parallel, then the 3 points are collinear. So let's find AB. So AB, we're going to use the method end minus start. So end minus start, so it's ending at the point B, so that's 3, 6, 7. It's starting at the point 1, 2, 3. So AB is 3 minus 1 is 2, 6 minus 2 is 4, 7 minus 3 is 4. So AB is 2, 4, 4. And let's go for AC. So AC equals, we're going to do end minus start here. So it's ending on C, which is 5, 10, 11. And it's beginning on point A, 1, 2, and 3. So this is 5 minus 1 is 4, 10 minus 2 is 8, 11 minus 3 is 8. So can we show that AB is parallel to AC? Well, if they're parallel, I can find some consistent lambda, which means that AB, lambda times AB equals AC, which means that some multiple of the vector AB gives me AC. So let's investigate and see if we can find a consistent lambda for each one of these components. So I'm going to say lambda multiplying AB, 2, 4, 4, equals AC, 4, 8, 8. And let's look at each one of these components in turn. So I have 2 lambda equals 4, 4 lambda equals 8, and I have 4 lambda equals 8. Now, if it's consistent and it works, I should be able to use one value for lambda for each one of these equations. So if I solve this first one, if I divide by 2, I have lambda equals 2. And then we're going to check to see if lambda equals 2 works for these other two equations. So for this one, 4 times 2 does equal 8. And actually that second equation is identical, so 4 times 2 equals 8. So there is a lambda that works. I can say 2 multiplies 2, 4, 4 equals 4, 8, 8. So I can say AB is a multiple of AC, therefore AB is parallel to AC, therefore the 3 points are collinear. They're all on that same straight line. Let's do this challenge question. So I've got A, B and C are collinear, find the value of K. Well, if they are collinear, I know that AB is going to be some multiple of AC. So let's find those two vectors first. So AB, we're going to do end minus start. So it's ending on B, 4, 10, 1, minus the start, which is going to be point A. So 1, 4, negative 2. So this vector is going to be 4 minus 1 is 3, 10 minus 4 is 6, 1 minus minus 2 is 1 plus 2, which is 3. So AB equals 3, 6, 3. And then let's look at AC. So AC is going to be, end point is K, 16, 4, minus the starting point, which is A, 1, 4, minus 2. So this vector AC is going to be K minus 1, 16 minus 4 is 12, 4 minus minus 2 is 4 plus 2, which is 6. Now, if they are parallel, I should be able to set up some value of lambda to make AB some multiple of AC. I could do it this way. I might actually, in hindsight, do it like this. I might say that there's some multiple of AB gives me AC. Either way is completely equivalent, as long as I can find some value, lambda, which means that one vector is a multiple of the other, it should work. So I think I'm going to do it this way around. So I'm going to say some multiple of 3, 6, 3 is giving me K minus 1, 12, and 6. And what we're going to do is we're going to investigate each component at a time, and we're going to find a value of lambda that works, and we're going to find a value of K that works. So if I look at my i's, I have 3 lambda equals K minus 1, so I've got 2 unknowns in that one. Then I've got 6 lambda equals 12, and I've got 3 lambda equals 6. And what I'm going to do is I'm actually going to solve these two for lambda, so I can see that there's a consistent lambda that works for both of these equations, which is lambda equals 2. So if lambda equals 2, that's 6 times 2 gives me that 12, and 3 times 2 gives me that 6. So lambda equals 2 works here. So I'm going to substitute lambda equals 2 into that top equation and choose K so that my vectors are consistently parallel. So 3 times 2 now equals K minus 1. So that's 6 equals K minus 1. So last but not least, we have K equals 7. Yeah, and we could check that works. So we could say 2 multiplies 3, 6, 3. Does that equal 7 minus 1, 12, and 6? Well, that's going to be, it'll stay on the left-hand side here. So 2 times 3 is 6, 6 times 2 is 12, 2 times 3 is 6. And let's have a look on this other side. Does that equal 7 minus 1 is 6, 12, 6. Yes, does work. Works. So for them to be collinear, K has to be 7.